Today is going to be a little bit more mathy than normal and get into some big terminology and all that sort of thing. Second order linear homogeneous recurrence relations with constant coefficients. That's a mouthful. Yeah, I see the looks on your faces. You're like, huh? Not really obvious from the name of the section what we're going to be dealing with today, but it'll explain them. Explain these relations as we get to it. A second order linear homogeneous recurrence relation with constant coefficients is a recurrence relation of the form A sub k equals capital A times A sub k minus 1 plus capital B times A sub k minus 2 for every integer k greater than some fixed integer, where A and B are fixed real numbers with B not equal to 0. So second order means there's two coefficients. Linear means there's no squared or cubed. Its recurrence relation will be shown a little bit, and the constant coefficients A and B are constant values. So state whether each of the following is a second order linear homogeneous recurrence relation with constant coefficients. Well, the first one has constant coefficients, and it has for A and B, and the A sub k minus 1 and A sub k minus 2 are both present. So yes, that would be the mouthful. Here, you have constant coefficients, 1 for each of them, but you have 3 of them, 3 terms. So this would be a third order linear homogeneous recurrence relation with constant coefficients, not a second order one. So that would be no. Here we have rational numbers, which are real numbers. So in the coefficients A and B, 1/2 and minus 3/7, and the C sub k minus 1 and C sub k minus 2 are both present. So yes, that is a second order linear recurrence relation. D, the coefficients are squared, or the term is squared or multiplied, so it's nonlinear. So that would not be a linear homogeneous recurrence relation. E sub k equals 2 times E sub k minus 2. That is a second order linear homogeneous recurrence relation where A equals 0. A is allowed to be equal to 0, so that would be allowed. F sub k equals 2 F sub k minus 1 plus 1. In this situation, B would be a 0, and that's not allowed for a second order linear recurrence relation, so that would be no. Here, A and B equal 1. All the other criteria are met, so yes, that would be a mouthful relation. And finally, h sub k equals minus 1 times h sub k minus 1. And then b is not a constant number, so it doesn't have the constant coefficients. So it would not be the second order linear recurrence relation with constant coefficients. So, and it goes through it, why each one is yes and no, but it alternates yes, no, yes, no, yes, no, and yes, no. Non-constant coefficients being the last one. All right. The distinct roots case. Let a and b be real numbers. A recurrence relation of the form a sub k equals capital A sub k minus 1 plus b times a sub k minus 2 for every integer k greater than or equal to 2 is satisfied by the sequence 1, t, t squared, t cubed, etc. to tn, where t is a non-zero real number if and only if t satisfies the equation t squared minus at minus b equals 0. Given a second order linear homogeneous recurrence relation with constant coefficients, this equation, given this relation, the characteristic equation of the relation is t squared minus at minus b equals 0. Consider the recurrence relation that specifies that the kth term of a sequence equals the sum of the k minus 1 first term plus twice the k minus 2 term. That is, a sub k equals a sub k minus 1 plus 2a k minus 2 for each integer k greater than or equal to 2. Find all sequences that satisfy the relation and have the form 1, t, t squared, t cubed, etc. to tn and so on, where t is non-zero. By Lima 581, relation 583 is satisfied by the sequence if and only if t satisfies the characteristic equation t squared minus t minus 2 equals 0. Since t squared minus t minus 2 equals t minus 2 times the quantity t plus 1, the only possible values of t are 2 and negative 1. A little factoring there from algebra. It follows that the sequences 1, 2, 2 squared, 2 cubed, etc. to n, and 1 minus 1, minus 1 squared, minus 1 cubed, minus 1 to the n are both solutions for the relation, and there are no other solutions of this form. Yeah, it just follows that these sequences are both solutions for the relation, and there are no other solutions for this form. Note that these sequences can be written more simply as 2 to the n for n greater than or equal to 0, and minus 1 to the n greater than or equal to 0. Lima 582. If R 0, 1, 2, 3, etc., and S 0, 1, 2, etc. are sequences that satisfy the same second order linear homogeneous recurrence relationship with constant coefficients. If C and D are any numbers, then the sequence A sub 1, A sub 0, A sub 1, A sub 2, etc., defined by the formula A sub n equals CRn plus DS sub n for every integer greater than n greater than or equal to 0, also satisfies the same recurrence relation. Consider the recurrence relation that specifies that the kth term of the sequence equals the sum of the k minus 1 term plus twice the k minus 2 term. The same relation we saw a little bit earlier. Find a sequence that satisfies the recurrence relation that also satisfies the initial conditions a sub 0 equals 1 and a sub 1 equals 8. Well, you consider the following sequences. They both satisfy the relation, although neither satisfies the given initial conditions. However, by lemma 582, any sequence that A that satisfies the explicit formula a sub n equals c times 2 to the n plus d times minus 1 to the n, where c and d are numbers, also satisfies the relation. So you can find c and d so that the sequence A satisfies the initial condition specified in this example by substituting n equals 0 and n equals 1 into the equation and solving for c and d, like so. When you simplify, you obtain the system 1 equals c plus d and 8 equals 2c minus d, which can be solved in various ways. For instance, if you add the two equations, you get 9 equals 3c, or c equals 3. Then by substituting into 1 equals c plus d, you get d equals minus 2. It then follows that the sequence a 0, 1, 2, etc., given by a sub n equals 3 times 2 to the n plus 2 minus 2 times minus 1 to the n, or 3 times 2 to the n minus 2 times negative 1 to the n for each integer n greater than or equal to 0. Satisfies both the recurrence relation and the given initial conditions. Like I said, this material gets a little bit more mathy in solving systems of equations, and we'll get into the quadratic formula a little bit later. Suppose the sequence A satisfies the recurrence relation, the base relation we saw earlier, for some real numbers a and b, with b not equal to 0, and every integer k greater than or equal to 2. If the characteristic relation or equation t squared minus at minus b equals 0 has two distinct roots, then the sequence A is given by the explicit formula a sub n equals c times r to the n plus s to the n, where c and d are numbers whose values are determined by a0 and a1. The Fibonacci sequence, covered last time, I believe. The sequence of the recurrence satisfies the recurrence relation f sub k equals f sub k minus 1 plus f sub k minus 2, with the initial conditions f sub 0 and f sub 1 equal 1. Find an explicit formula for the sequence. The Fibonacci sequence satisfies the first part of the hypothesis of the distinct roots theorem, since the Fibonacci relation is a second-order linear homogeneous recurrence relation with constant coefficients. A equals 1 and B equals 1. To check that it satisfies the second part of the hypothesis, examine the characteristic equation t squared minus t minus 1 equals 0. By the quadratic equation, quadratic formula, t equals 1 plus the square root of 5 over 2, or 1 minus the square root of 5 over 2. And so the roots are distinct. Thus it follows from the distinct roots theorem that the Fibonacci sequence is given by the explicit formula f sub n equals c times 1 plus 5, the square root of 5 over 2 to the nth power, plus d times 1 minus square root of 5 over 2 to the nth power for each integer n greater than or equal to 0, where c and d are the numbers whose values are determined by the fact that f sub 0 and f sub 1 equal 1. So, some sticky math. Lots of symbols and mouthfuls and all that sort of stuff. Basically, f sub 0 equals c plus d. And f sub 1 equals c and d times the two roots that we found earlier. Okay? Thus, the problem is to find the number c and d such that c plus d equals 1, and this here equals 1. May look a little complicated, but in fact it is just a system of two equations within two unknowns. By solving this two system of equations, we get c equals 1 plus the square root of 5 over 2 times the square root of 5, and d equals minus the quantity 1 minus the square root of 5 over 2 times the square root of 5. Substituting these values for c and d into the formula gives this monstrosity, or simply this, if you can call that simple, for each integer n greater than or equal to 0. Remarkably, even though the formula for f sub n involves the square root of 5, all of the values of the Fibonacci sequence are, in fact, integers. Now, the single root case. Let a and b be real numbers, and suppose the characteristic equation t squared minus at minus b equals 0 has a single root. Then the sequences 1, r to the first, r to the second, r to the third, etc., and 0, r, 2r squared, 3r cubed, etc., both satisfy the recurrence relation a sub k equals capital A sub k minus 1 plus b times a sub k minus 2 for each integer k greater than or equal to 2. Theorem 585. Single root theorem. Suppose the sequence satisfies the recurrence relation given here for some real numbers a and b, with b not being equal to 0, and for every integer k greater than or equal to 2. If the characteristic equation t squared minus at minus b equals 0 has a single real root, then the sequence A is given by the explicit formula a sub n equals c times r to the n plus d times n times r to the n, where c and d are real numbers whose values are determined by the values of a, 0, and any other known value of the sequence. Suppose a sequence B satisfies the recurrence relation b sub k equals 4b sub k minus 1 minus 4b sub k minus 2, with initial conditions b sub 0 is 1 and b sub 1 is 3. Find an explicit formula for b sub 0, b sub 1, b sub 2, etc. This sequence satisfies part of the hypothesis of the single root theorem because it satisfies a second order linear homogeneous recurrence relation with constant coefficients a equals 4 and b equals minus 4. The single root condition is also met because the characteristic equation t squared minus 4t plus 4 equals 0 has the unique root r equals 2. So it follows from the single root theorem that the sequence B is given by the formula b sub n equals c times 2 to the n plus d times n times 2 to the n for each integer n greater than or equal to 0, where c and d are the real numbers whose values are determined by the fact that b sub 0 equals 1 and b sub 1 equals 3. To find c and d, you write it out this way, where c equals 1 and 3 equals 2c plus 2d. Substitute c1 into c equals 1 into the second equation, and you get d equals 1/2. Now substitute c equals 1 and d equals 1/2 into the formula to conclude that b sub n equals 2 to the n plus 1/2 n times 2 to the n, or 2 to the n times the quantity 1 plus n over 2. So, yeah. Like I said, this one was a little bit more mathy than previous sections that we've done. And I'll be quite honest, I'm surprised I didn't stumble over my words when talking about the second order, whatever, linear, homogeneous stuff. But this next section has some problems in it. When I was reviewing the section, I came across some typos and I couldn't figure out what it should have been saying. So some of the equations don't make a lot of sense in one particular example that they give. So we'll just kind of skip that one. I'll try to figure it out later. General recursive definitions and structural induction. Sequences of numbers are not the only objects that can be defined recursively. In this section, we discuss recursive definitions for sets and functions. We also introduce structural induction, which is a version of mathematical induction that is used to prove properties of recursively defined sets. Recursively defined sets. To define a set of objects recursively, you identify a few core objects as belonging to the set and give rules showing how to build new set elements from old. More formally, a recursive definition for a set consists of the following three components. The base, which is a statement that certain objects belong to the set. A recursion, which is a collection of rules, not necessarily just one, but it could be more than one rule, indicating how to form new set objects from those already known to be in the set. Finally, there's a restriction, a statement that no objects belong to the set other than those coming from the base and the recursion. The set of Boolean expressions was introduced in section 2.4 as legal expressions involving letters from the English alphabet such as P, Q, and R, and the symbols for and, or, and not, and parentheses. To make precise which expressions are legal, the set of Boolean expressions over a general alphabet is defined recursively. The base is each symbol of the alphabet is a Boolean expression. Recursion. If P and Q are Boolean expressions, then the following are also Boolean expressions. P and Q is a Boolean expression. P or Q is a Boolean expression. Not P is a Boolean expression. And P in parentheses is a Boolean expression. So that's 4 rules of recursion that it gives. Like I said, the rules for recursion aren't necessarily just one, but it could be many different rules to define the recursion. Restriction. There are no Boolean expressions over the alphabet other than those obtained from the base and the recursion. Derive the fact that the following is a Boolean expression over the English alphabet. And gives this expression here. Well, by L, P, Q, and R are Boolean expressions. Or I'm sorry, by rule number 1, P, Q, and R are Boolean expressions. By 1, 2A and 2C, P and Q are and not R are Boolean expressions. By 2, 2D, and 2A, P and Q in parentheses, and not P and P, I'm sorry, not R and P, kind of hard to read that, are Boolean expressions. And 4 by 3 and 2C and 2D, not P, not quantity P and Q, and not R and P in parentheses are also Boolean expressions. Therefore, by 4 and 2B, the full expression is a Boolean expression. Certain configurations of parentheses in algebraic expressions are legal, such as these two here, whereas others are not. such as these two here. Here is a recursive definition to generate the set C of legal parentheses structures. Base, an open and closed parentheses, is in C. Recursion. If E is in C, so is E in parentheses. If E and F are in C, so is EF. Restriction. No parentheses structures are in P other than those obtained from the base and the recursion. Show that this here is a parentheses structure in C. Well, by 1, the open and close is in parentheses. Open and close parentheses is in C. By 1 and 2a, this is also in C. And then by 2, 1, and 2b, the final expression is in C. Going back to the rules of the recursion here and the base. Recursion is used to give a formal definition for the set of all strings over a finite set. Why that was put in on the side, I have no idea. Okay, general recursive definitions and structural induction. Recursive definition for the set of all strings over a finite set. Let A be any finite set. Call the elements of A characters and define the set S of all strings over A as follows. Base condition. Lambda is a string in S where lambda denotes the null string or the string with no characters. The recursion. 2. New strings are formed according to the following rules. 2a, if A is any string in S, and if C is any character in A, then UC is a string in S. UC is a string in S. Where UC is called the concatenation of U and C, and is obtained by appending C on the right of U. Rule 2b. If U is any string in S, then both the concatenation of lambda and U, denoted by lambda U, and the concatenation of U and lambda, denoted U lambda, are defined to equal U. Symbolically, lambda U equals U lambda equals U. Basically, concatenating the null string to any string gives you the original string. If U and V are any strings in S, and if C, this is rule 2C here. If U and V are any strings in S, and if C is any character in A, then the concatenation of U and VC is defined to equal the concatenation of UV and C. Basically, it's associative. The associative property applies to concatenation as well. Finally, the restriction. Nothing is a string in S other than objects obtained from the base and the recursion. The base for the recursive definition of strings only indicates that one character, namely lambda, is a string. The next theorem states that each individual character in this underlying set is a string. If A is a finite set and S is the set of all integers over A, then every character in A is a string in S. So each character is its own string. Suppose A is a finite set, S is the set of all strings over A, and A and B, little a and little b are in A. Because of the way of the definition of the string is stated, it cannot be deduced immediately that B, parentheses, open parentheses, A, close parentheses, is a string in S. To prove that this is true, first show that BA and BA in parentheses concatenated with A are strings in S, and use the fact that that the associative property is applicable. First, by theorem 591, A and B are strings in S because both A and B are in A. By 1 and 2A, BA is a string because in S because B is in S and A is an element of A. By 2 and 2A, BA in parentheses A is a string because S in S because BA is an element of S and A is an element of big A. By 2C, B, the associative property applies because B and A are strings in S and A is an element of big A. By 3 and 4, B, AA is a string in S because it equals B, A concatenated with A, which is a string in S. Proving properties about recursively defined sets. When a set has been defined recursively, a version of mathematical induction called structural induction can be used to prove that every object in the set satisfies a given property. Structural induction for a recursively defined set. Let S be a set that has been defined recursively, and let P of X be a property that objects in S may or may not satisfy. To prove that every object in S satisfies P of X, perform the following two steps. The basis step, prove that P of A is true for each object A in the base for S. And then the inductive step, show that for each X in S, if P of X is true, and if Y is obtained from X by applying a rule from the recursion, then P of Y is true. To perform this step, suppose that X is an arbitrarily chosen element of S for which P of X is true. This is the inductive hypothesis. Then show that if Y is obtained from X by applying a rule from the recursion for S, then P of Y is true. Conclusion. Because no objects other than those obtained from the base and recursion are contained in S, steps 1 and 2 prove that P of X is true for every object S in X in S. Let S be the set of all integers defined recursively as follows. Base 4 is in S. This is the example that gets screwy. This equation is not right because n plus 3 for any integer n is basically 4, 5, 6, 7, 8, 9, 10, etc. If I'm not mistaken, right? If n is any integer, n plus 3 is, and the base is 4, it would be 4, 5, 6, 7. Yeah. Use structural induction to prove that for every integer n, n mod 3 equals 1. No, it's not true. Because it would just be now there's a typo going on here. I'm not sure where, because it goes into this proof where it says P of 4 is true because 4 times 3 is 3 times 1 plus 1. So 4 mod 3 is 1. But where did it get the 3 times 1? And the recursion for S consists of only one rule, and the rule is applied to N. The result is N plus 3. How did the inductive hypothesis become N equals 3K plus 1? Yeah, it completely lost me too. So I'm just kind of, or they're just not catching typos in the publication process of these slides. Yeah, but we've seen typos before on the thing. So go to the next example. A recursive definition can also be given for the length of a string. Given the set of all strings S over a finite set A, the length L of a string in S is defined as follows. The length of lambda equals 0. For every string U in S, and for every character A in A, the length of UA is one more than the length of U. Can you keep it down a little bit? Can you keep it down a little bit? Length of UA is length of U plus 1, where U is an element of S and A is an element of the alphabet. The following theorem states that the length of a concatenation of two strings is the sum of the lengths of the strings. Additive property of string length. If S is the set of all strings over a finite set A, then for all strings U and V in S, length of the concatenation of U and V equals the length of U plus the length of V. The next theorem extends the operation to pairs of strings. The concatenation of any two strings is a string. If theorem 593, if S is the set of all strings over a finite set A, and U and V are any strings in S, then U concatenated with V is a string and is also a string in S. The next theorem generalizes the associativity of concatenation to any three strings. If S is the set of all strings over a finite set, and U, V, and W are any strings in S, then U concatenated with V concatenated with W equals U concatenated with V concatenated with W. Associative property applies here. Recursive functions. A function is said to be defined recursively or to be a recursive function if its rule of definition refers to itself. Because of this self-reference, it is sometimes difficult to tell whether a given recursive function is well defined. Recursive functions are of great importance in the theory of computation in computer science. The following function, m is an element of positive integers, was defined by John McCarthy, pioneer in theory of computation, and apparently in the study of artificial intelligence as well. M sub n is equal to n minus 10 for if n is greater than 100, and m of n equals m of n plus 11 if n is greater than or less than or equal to 100 for all positive integers n. So, by repeated use of the definition of m, m 99 equals 91. The remarkable thing about this function is that it takes the value 91 for all positive integers less than or equal to 101. This is an exercise at the end of this section. For n greater than 101, m of n is well defined because it equals n minus 10. In the 1920s, the German logician and mathematician Wilhelm Ackermann first defined a version of the function that now bears his name. This function is important because its values are computable but cannot be evaluated using only 4 next loops. The function is defined on the set of all pairs of non-negative integers as follows. A of 0, n equals n plus 1 for all non-negative integers. A of m, 0 equals a of m minus 1, 1 for all positive integers m. A of m, n equals a of m minus 1, a of m, n minus 1 for all positive integers m and n. Find a of 1, 2. Well, just do a lot of substitution and following the definitions of each one, and then you get 4 at the end by substituting with these 1, 2, 3 different rules. You get 4 at the end. The special properties of the Ackermann function are a consequence of its phenomenal rate of growth. While the values of a 0, 0 and 1, equals 1, and a 1, 1 equals 3, a 2, 2 equals 7, and a 3, 3 equals 61 are not especially impressive, but a sub 4 of 4, 4 is approximately equal to 2 to the second to the 65,536th power. Then they get really big. Yeah, that's kind of a big number, but yeah, it just grows beyond exponentially. It grows incredibly fast. Considering the following attempt to define a recursive function g from positive integers for each integer greater than or equal to 1, G of n is equal to 1 if n is equal to 1. G is equal to 1 plus g n divided by 2 if n is even. And g of 3n minus 1 if n is odd and n is greater than 1. Is G well defined? Well, suppose G is a function. Then by definition of G, these values can be obtained for G of 1, G of 2, G of 3, G of 4, etc. All right. However, G of 5 equals G of 14, which equals 1 plus G of 7, which equals 1 plus G of 20. Why is that so? Oh, okay, yeah. Okay. G, if you go back to the definition, G of an odd number is 3n, it's G of 3n minus 1. So G of 5 is the same as G of 14, which is 1 plus G of n over 2, which equals 1 plus G of 3n, here being 7, minus 1 is G of 20. So keep going through the substitutions and all that sort of stuff, and you get 3 plus G of 5, which is back to where you're going from. And so if you were to say 3 plus G of 5 equals G of 5, subtract G of 5 from both sides, you get 0 equals 3, which is false. It follows that G is not a function. So you get into, if you were to implement this in a loop in a program, it would get into an endless loop trying to calculate this repeatedly and over again. It would be never ending. So you have to be careful how you define recursively defined functions, so you don't end up with infinite loops and stack overflow problems and that sort of thing. Anyway, that should be about it for today. Have a wonderful afternoon. Enjoy your weekend. And see you on Tuesday for the quiz on Chapter 5. So please be on time so we can get that done and start a lecture afterwards. Have a good day.